Worthwhile to show how those Maxwell relations can be used in practice to get some sort of useful relationships. Now what I've done is I have rewritten all of the Maxwell relations that come from the 4 thermodynamic potentials up here at the top of the page so that we have them there for reference, and you'll be able to use those for reference anytime you need them for anything in this course. Don't worry, it'll be a limited number of opportunities that you would need them. Now, what I want to do is explore, though, how we might use this to get a meaningful expression for the internal pressure. And I want to remind you that we defined some time ago the internal pressure, this is back in Module 1, as equal to this partial derivative. It was a partial derivative of the internal energy with respect to volume at constant temperature. And remember, at that time we mentioned that for an ideal gas that this would be 0 most likely, because this really arises from the intermolecular forces that act between the atoms in a gas, or the particles in a gas. Now, in order to get a handle on this, I'm going to somehow need to express my internal energy as a function of temperature and volume. Now, we know those aren't the natural it would be naturally entropy and volume would be the natural variables, but we can still write a total differential for this particular kind of function. And if I do that, I'll end up with an expression that is du dt at constant volume dt plus du dv at constant temperature dv. Now notice what we have here. This internal pressure is actually appearing here in this total differential. And also this term here we might recognize as the heat capacity at constant volume. But now what I'm going to do is I'm going to want to compare this with the differential expression that we have gotten in its natural variables, which look like this. Alright, we can't just assume because we've got a dv here and a dv here that this negative p is equal to this derivative. That doesn't work quite that way. Alright, so instead, what we're going to need to do is find a way to express this ds in terms of the two variables that are used here. So in other words, I'm going to have to write out a total differential for s as though it's a function of temperature and volume. So it'll look very similar to this. It'll be ds dt at constant v dt and ds dv at constant temperature dV. Now what I'm going to do is I'm going to take this expression and substitute it in here for ds. Alright, so that's all I'm going to do. I'm going to rewrite this other stuff, but I'm going to use this CV to simplify it a little bit. So I'm going to have in the end an expression for the total differential of du that will look like CV dt plus this derivative that I'm most interested in, du dv at constant temperature dv, and I'll just remind you that is the definition of that internal pressure that we're interested in. But now I'm going to write it, I'm going to write this other side from this initial differential using our explicit expression here for ds, the total differential of the entropy. So I'm going to have temperature times this term, ds dt at constant volume dt, plus t times this term, ds dv at constant temperature dvolume, minus p dvolume. Now I'll be able to combine these last two terms because they're both in terms of dv. But I want to focus on this term right here because in fact it appears up here in the Maxwell relation that arises from Helmholtz energy. And I can see that from this I have it equal to the derivative with respect to pressure of pressure with respect to temperature at constant volume. Now why might I care about that? Well, although we, I hope, are getting increasingly comfortable with entropy as a physical property, I don't really know how to do these derivatives, but if I have an equation of state for a gas, I can certainly evaluate the derivative of the pressure with respect to temperature at constant volume. So this is something that in principle is more accessible for calculational purposes. So now if I substitute that in, I'll end up with this expression t ds dt at constant volume dt plus, I'm going to have a compound thing here, T times this new derivative that's equivalent to this derivative, dP dt at constant volume minus the pressure, and all of this is going to be multiplied by dV. Now remember, this was equal to our expression here on this side of the equation. So in fact, I can relate this CV to the stuff that's multiplying by dt. Both of these are dt. So from that I would have CV is equal to T times this partial derivative of the entropy with respect to temperature at constant volume. But that just means that ds dt at constant volume is equal to 1 over T CV. This is actually a result that we got before, so it should look familiar. And this was the result that we used to integrate to find an absolute entropy. So very reassuring that we're getting the same answer here. All right, the other thing here, though, is that this term is going to be associated with this. So in other words, I'm going to have my internal pressure, which is defined as UdV at constant temperature, is now going to be equal to this thing in brackets. And in fact, this now is an expression that I can use to calculate my internal pressure given the equation of state or other information about the system, because all of the quantities in this expression are in fact quantities that I can presumably measure or get a handle on, which is very interesting because now we can get a direct piece of information about the intermolecular forces that arise from the intermolecular forces for this internal pressure directly from measurements that we can make on physical quantities.